So, let's begin. What is curtailment? Curtailment is the enforcement of production reduction in the case of energy production due to the grid's saturation. Curtailment needs to be calculated to manage losses and improve future assessments. We will see later why. What does curtailment look like? When the grid reaches or approaches saturation, it enforces curtailment of the energy production. For each station, it sets an upper limit for production at that time. This reduction can even reach zero. This upper limit would be this red dotted line. The curtailment would be anything above that upper limit, and our actual power export would be anything below this upper limit. And how do we calculate these losses? As we saw before, the enforced upper limit is the object by which curtailment occurs. So this upper limit is not necessarily curtailment. If we have an upper limit, though, doesn't mean that it affected the production. Maybe the upper limit is over the projected exportation, which means there were no losses. Or maybe the projected exportation is higher than the set point, which does mean we had losses, but nothing guarantees us that these losses were due to curtailment. So, in order to protect the grid from overproduction, operators may enforce a set point on producers. This set point, or SP, acts as a limit to how much each producer can produce. Every production that is cut off due to this set point is called curtailment. So we can safely assume that if a set point is enforced by an operator, it doesn't necessarily mean that a curtailment is also at play for the producers. And why do we need to calculate these curtailments? We need to know our total curtailed energy production because the regulatory authorities have made a contract for that day in which a specific number of production is agreed upon. If the operator decides that they don't need suddenly all that energy, the producer will get paid the difference, so they will be compensated. So let's discuss about how we can calculate these curtailments. So let us begin by talking about how we can understand what curtailment is. To do that, we will use three data. These data are a projected production, which is what we expect to produce. This projected production is calculated the day before the actual production, which is another one of our data points. And lastly, we have the actual production without curtailment. In every case, we will have these two. These two are necessary for a SCADA or measuring application to exist. But this actual production, which already takes into account the curtailment losses and basically says that, this is what you would have produced during this actual production period, doesn't exist. This is something made up for us to understand how curtailment is calculated and what exactly it is. So if we zoom in this diagram, we will see this. If we follow these three lines, we will see that the blue is the projected production, which is a really good simple line. We will see the actual production, which is the red line. We can see that it mostly follows the actual production without curtailment until this period. This is our interest period. This is what interests us. We can see that the red line splits and basically becomes a straight line until it's not, until it starts again to follow the purple line. The purple line, on the other hand, follows a random logic of production for the day. So this does make sense. This makes a lot of sense for us. But the actual production doesn't, because in no way can an actual production or a natural production of a, let's say, solar farm be a straight line. it can't do that. It is unpredictable, and that is the reason we have operators and regulatory authorities, etc. So, this difference between the actual production without curtailment, this theoretical line, and the actual production, which is the red one, this surface area in between these two lines is the curtailments. We can see that it is the surface area of the first line and the third line. And all the other differences with projected production and actual production without curtailment, all the other differences besides curtailments are all the other losses. And these are the surface areas of the first line and the second line. Of course, curtailments plus all the other losses, so every difference is considered all the losses in general. Curtailment is only applied if we have sufficient production to begin with. So even if a set point is enforced, even if the operator decides to enforce a set point, a maximum production point, it has no effect if my production is already lower than that point, which makes sense. Curtailment may not make sense 100% at this point, but it is a difficult thing to explain. So we will follow a process to make it easy for everyone to accept, to better understand what we talked about before, what curtailment is, and dive into what makes a curtailment, basically a curtailment. We will use the filter analogy, which is an analogy I created to hint at what curtailment does and how we can derive some elements from it. Let's say that we have this filter, and let's say that this filter allows signals of frequencies in the range of 0 to 50 Hz. That means the maximum allowed frequency, or the set point that we talked about before, is 50 Hz. Let's also assume that this low-pass filter sets the frequencies of all the unfit signals to that maximum 50 Hz. So if a signal comes that is 60 Hz, which is above the maximum point, it reduces its frequency to 50 Hz. And let's also assume that a series of random signals, mostly different frequencies, passes through that filter. So after that filter, after every signal has passed through our low-pass filter, we will have these, let's say, 7 signals. Let's say 7 signals pass through the filter, and this is what we have to show for it. 7 signals, the first one of 50 Hz, the second one of 25 Hz, third one of 50, 32, 15, 49, 23. 2 of them are exactly at 50 Hz, which is our set point, our maximum allowed frequency. So if we had to guess which of these signals was most likely affected by the low-pass filter, and why? The correct answer is that the most likely signals to have been affected by the low-pass filter are the first signal and the third signal. These are, of course, the 2 signals that are exactly at the maximum allowed frequency of 50 Hz. But why is that? Since random signals are being fed through the low-pass filter, it is almost impossible that these 2 signals were exactly the enforced upper limit, 50 Hz. It is more likely that these signals were greater than 50 Hz originally, and were curtailed down to 50 Hz, which was one of the properties that we allowed our filter to have. So, in this example, the set point was the upper limit of the low-pass filter. The actual production was the signal we saw after the low-pass filter, and the projected production was the original frequency of these signals. If we had to make this an exercise, we would say that the SP, or set point, was 50 Hz. The signals after the low-pass filter were the actual production, and there were 7 signals. These were their frequencies. And before the low-pass filters, we had the projections of these 7 signals, and we can see these were ranges. So the first signal was before the low-pass filter around 90 to 100 hertz, and the second signal was around 20 to 30 hertz. So we said that it was most likely that the first and third signals were affected by the low-pass filter and thus curtailed. So in order to calculate this curtailment, we would say that for the first signal, the curtailment was its projected hertz, so 90 to 100, let's say 95, minus its actual hertz, the one that it was curtailed down to. So 95 minus 50 hertz equals 45 hertz. The curtailment of the third signal was similarly 65 minus 50, 15 hertz. So the total curtailment was 45 plus 15 equals 60 hertz. And if that hertz was, let's say, energy, then the operator would have to pay us back for that 60, in quotation marks, hertz as per contract. Of course, right now we consider curtailment if something is exactly on the set point, but in real life this is not possible, and we just say that the curtailment is enforced if it is very close to that set point. So if we combined all of this knowledge into one single thing, we can take this code. This code was created by myself for an organization, for a company, which I obviously for legal reasons can't say which it was, and I created this algorithm so that they can calculate the curtailments that were enforced upon their energy production for their solar and wind farms. Of course, they wanted these calculations to better understand what they can actually offer to the grid, but mostly wanted this knowledge to take it to the operator and say, hey, you curtailed me about, let's say, this much kilowatt hours, and you need to pay me back as per contract, because we agreed upon this production, I provided you this production, and you denied taking every bit of it. So in this code we have these parameters, these variables. The first one is SP, the set point, which is enforced by the operator when the grid is saturated. N1 is a percentage greater than 100%. It is a space for equipment errors, which we talked about before, that in real life we can't have exactly the set point, and we have to take into account the errors. N2 is lower than 100%, and it is the lower space for equipment errors. Exported power is the actual production that we feed into the grid. Projected power is the power that we expect to produce. And curtailment is the curtailment for that time period. And I say time period because in solar and wind farms and every other power production company or plant, the SCADA or the measuring applications, they send us data in time periods. So for example, for time period 1, I had a set point A. So I had a set point A, it was an active set point, and I had B be my exported power, and C be my projected power. So these are the three most basic variables in every measuring unit for our solar or wind farms. And this is what makes this algorithm very good. It is simple and uses variables that most applications have. So let's talk about the algorithm. If exported power is less than or equal to this space for equipment errors times the set point, and if the exported power is greater than or equal to this lower space for equipment errors times the set point, then if the exported power is less than the projected power, then the curtailment would be equal to our projected power minus the exported power. Don't worry, we will explain what everything is with examples. Else, the curtailment would be zero and thus not exist. So, let's explain what this algorithm does. We have the set point being this straight line in the middle. We have the exported power being somewhere around this set point. We have these brackets, the bracketing effect of the algorithm, which is the upper and lower space for equipment errors, which is needed for real-life applications. And this dark blue line up here is our projected power. So what does the algorithm exactly do? It says this: if I have a set point and my expected power is very close to this set point, and of course if I have a difference in projected power and exported power, if I were to export more power than I actually do, and there is a set point which I'm close to, then there was curtailment, and the curtailment was this difference, this surface area. So, for example, in this point, my exported power was within the bracketing of the set point, and I did have a difference of projected power with my exported power, which means that I did have a curtailment of this difference. This was my curtailment, this altitude, this height, and that's basically what the algorithm does for every period. A period may be this one also. You see, it's quite different, but it works for every period of the day, which is thousands of periods. And let's say also that we have an example with numbers. And let's say that the set point is 500, exported power was 250, projected power was 550, N1 was 105%, so we are 5% above the set point, and N2 was the lower space for equipment error, which would be minus 5%, 95% of the set point. This is the bracketing, and we would begin to check if this is true, if these things are true. So, is my exported power less than or equal to N1 times my set point? So, is 250 less than or equal to 105% times 500, 525? Yes, but is my exported power also greater than or equal to N2 times my set point? So is 250 greater than or equal to 475? No. So immediately I go to this condition and conclude that my curtailment is zero and thus non-existent. And it makes sense, because we said before that curtailment is enforced if the set point is really close to my exported power. We can safely assume that we have a curtailment if the set point is really close to that exported power. And in this case, my set point was far away from the exported power, 250 units apart. So it makes sense. If we take this 250 and say that it was 505, then things would be different. So I take 505 and put it in these two equations. Here we can see that 505 is less than or equal to 525, but 505 is also greater than or equal to 475, so we check that box too. And then we would continue. Is my exported power less than my projected power? Yes, 505 is less than 550. So we move down and say that we do have curtailment, and my curtailment is equal to projected power, so 550, minus my exported power, 505. So that means I have a curtailment of 45 units. And you can test the logic of the algorithm however you like and see that it works. You can play around with the bracketing, make it smaller or bigger in the upper or lower side, and see that it still works fine. And it does work fine, because I tested it in the company alongside other algorithms and concluded based on results that it was somewhere around 5 to 6% close to reality, which is amazing considering that every other option was around 50 to 1000% close, which is not close at all. It's very far away actually. In this Excel sheet I created for the company I talked about before, I explain why my method was closer to reality and thus better for the operator, better for the compensations. Here we can see 4 different tests. I made a percentage test, a meteorological test, which is a prediction application and algorithm, and kilowatt peak algorithm, which uses the maximum power production of the plant. And then there was the bracketing method, which is the one I created from the beginning, and the one that I'm showing to you. It seems 6.3% close to reality, and used hundreds of thousands of time periods to make this percentage, so you can clearly see that it works. All the other methods, you can say they did work. You can see that they could be close. I mean, a company which doesn't really care for precision could say that, yeah, 50% is okay for me, but it's not, because the logic is wrong. So maybe you got lucky and had 50% in this year, but in the next year maybe this would skyrocket and you would see much different results. And in this case I don't use for these percentages the January and September months, because they were problematic and they had problems with the measuring units, so they're not very trustworthy. That's the reason why January is red and September is orange. This is the last point I'm going to make. It is the Excel I used to explain to the big heads that curtailment is simple yet complicated. Having explained all these things to you, it will be easy to understand this last point. So let's begin. These are the 2 diagrams. This is the curtailment diagram, which shows the production and the projections, and this is the losses diagram, which we will see later. The curtailment diagram shows our power export, our exported power, our actual curve expectation, which is something like the expected power but has taken into account multiple factors like weather or system failures, etc. So this is what we are going to use. This is more reliable. And the set point. So let me remove the expected power and just have the actual curve expectation. And what we can see here is that the set point is mostly above the whole surface area, and this has to do with the fact that the regulatory authorities make that contract. This contract is mostly made for the kilowatt peak, as we say, the peak production of that solar or wind farm. So that is why it is mostly above our projections and productions, because they had already taken into account these operators, these regulatory authorities, that I have this much to offer, so you already know that. So when you have a set point in action, basically the set point already existed. When the set point is above our maximum production, we say that the set point is inactive. So it's there, but it doesn't affect my production, since I obviously can't produce more than my maximum capacity. When this set point drops below my maximum capacity, though, it becomes an active set point. An active set point is something to keep an eye out for. So we have two active set points. We have this one and this one. Let's focus on the first one. We go here where the set point is active. What do you think? Is there a curtailment or is there not? If you think about the things we talked about before, it will be easy. We said that if my power exportation is very close to the set point and there is a difference between my expected production and my actual exported power export, my exported production, then we do have curtailment. So in this case we do have curtailment. Our set point is active, it is close to my power export, and there is a difference between my expectations and my power production. On the other hand, we have this active set point, and we can see that the power export is nowhere near the active set point, although we have a curve expectation which is higher than my actual power export. This means that there are losses which my special curve did not account for, but these losses were not curtailment. So these are other losses, this surface area. This surface area is curtailments, and if I enable the expected power, this surface area, the difference between my special analysis curve expectation and my simple curve expectation, this difference between the grey and the orange lines is my other losses, or what I thought were losses, because in this case we can see that the power export follows my simple curve. So in this case the actual curve expectation, which is normally the better one, was worse. Of course nothing is perfect, and I meant to include that here in this diagram, and I can see that I seem to have other losses here, but in fact I don't. I don't have other losses because my actual production is over my actual curve expectation. So it would seem that only in this instance my special curve expectation was actually worse than my simple one, which is luck. Not everything is perfect and nothing works exactly as you want it to. And this is important to understand, especially in this field of algorithms. As we saw before, the best algorithm that we had in this company was 6.3% close to reality, but it wasn't 100% there. It wasn't 0% difference. And same goes for this. If we go to the other diagram now, we can see all the losses. The entire losses include both the curtailment and other losses, and of course we can see that the curtailment losses were this surface area, within these time periods, which we can clearly see. We were correct. And the other losses were here, this big surface area, these big spikes, but we also had other losses in the curtailment region, but above the surface area of the curtailment, right here. And that's everything you need and should know about curtailments, and how to calculate them efficiently and correctly.